Pluto, a distant and perplexing, more modest planet, was once a person from our nearby planet group's planetary family. However, later disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking revelation. They suggest that this chilly world is on a potential collision course with Neptune. In any case, how could this work out, and what may be the results of such a gigantic event? Are we seeing an intriguing, enormous peculiarity, or is there something else to this approaching, limitless accident? Join us as we explore the potential results of a Pluto-Neptune crash. Pluto, a past planet that was downsized to a dwarf planet mostly due to its irregular orbit, remains a subject of interest and study in the vast scientific community. According to recent expectations by leading specialists, Pluto's trajectory is hazardously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a potentially dangerous collision between these two planets that could be a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It requires a shocking 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its exceptionally elliptical shape, contrasting completely with the nearly circular orbits of the major planets. What makes Pluto's orbit even stranger is its tilt, determined at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets. This tilt and eccentricity add layers of complexity to its orbital pattern. One of the most captivating aspects of Pluto's orbit is its conjunction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to comprehend its unusual path. Unlike other planets whose orbits lie somewhat close to the ecliptic plane, Pluto's orbit protrudes with its steep inclination and odd shape. The mystery grew with the realization that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. Terms like asymptotic libration and degree libration, along with the VZK precession, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a kind of libration with respect to Pluto and Neptune. This term really means that when Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial factor in the situation is the VZK precession. This is named after three scientists, VAV, Apple, LV, and Chi, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. For Pluto's case, VZK helps us understand why its orbit around the Sun is so strange despite the apparent chaos. This precession helps keep Pluto's orbit stable for an exceptionally long time. The VZK precession shows that, although things in space might seem wild and erratic, certain patterns and rules keep everything in place. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or drift off course. This three-body problem helps us understand how these orbits evolve because of the way space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, Despite these stabilizing properties, Pluto's orbit is actually volatile, with minor deviations in initial conditions leading to enormous differences over millions of years. However, these erratic properties of Pluto's orbit have been found to maintain stability over long timescales. In fact, ongoing simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a large part in protecting Pluto's orbit. Additionally, Saturn helps as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an incredibly long time, perhaps even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These quirks are important in the larger context of the universe, as they help maintain the order and consistency of celestial body movements. Without these factors, our solar system would be a place of much greater disruption and unpredictability. Bodies like Pluto could potentially crash into others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions about it potentially impacting Neptune in the future, understanding its orbit is essential. This gives us a clearer image of the solar system's dynamic nature. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also demonstrates the importance of continuous observation and study of these phenomena to better understand our place in the universe. Understanding the depths of space often drives us to confront the unusual nature of celestial bodies, and Pluto's orbit is a perfect example of this eccentricity. The concept of orbital chaos, which refers to the fragile dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use complex mathematics to model how Pluto, along with other space objects like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even small changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something truly interesting about Pluto's orbit. Despite having features like asymptotic and latitude libration to stabilize it, its orbit can still be chaotic and erratic. If you start with even a small difference in where Pluto is or how fast it's moving, its path can end up looking completely different. However, despite this chaos, Pluto's orbit remains stable for an incredibly long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it may seem out of control at first. Predicting major events, especially when they involve turbulent orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While numerical simulations provide strong foundations to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we've made huge strides in understanding space, the case of Pluto reminds us that our knowledge of the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects on the stability and trajectory of other bodies within the system. So why are leading astrophysicists only now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event from occurring? Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the overlooked corners of space. Tyson's stance on Pluto's renaming is grounded in the continually expanding knowledge of our solar system. He views the renaming not as a downgrade, but rather as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views Pluto's orbit, as well as its interactions with Neptune, from a perspective that recognizes the capriciousness of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the distant future due to the ongoing gravitational interactions between it, Neptune, and the rest of the planets. In conclusion, Pluto's orbit is a fascinating case study in the complexities of celestial mechanics and orbital elements. While current scientific understanding suggests that Pluto is unlikely to crash into Neptune, the future remains uncertain. As space exploration and our understanding of gravitational forces continue to advance, we may gain further insights into the long-term behavior of these distant bodies. Until then, the mystery of Pluto and its potential future interactions with Neptune will remain an intriguing subject for astrophysicists and space enthusiasts alike. As we continue to study Pluto's orbit, it's clear that the factors influencing its path are far from simple. The interactions between Pluto, Neptune, and the other giant planets in the solar system form a delicate balance that has allowed Pluto to avoid crashing into Neptune, despite their intersecting orbits. Yet this balance does not come without its complexities and potential risks in the distant future. The gravitational pull of the outer planets, especially Neptune, plays a significant role in keeping Pluto on its current path. However, as astrophysicists like Neil deGrasse Tyson and Michio Kaku point out, these interactions are not static, they are constantly evolving. One of the key components of this evolving dynamic is the fact that the orbital paths of Pluto and Neptune, despite appearing to cross, are locked in a kind of cosmic dance called orbital resonance. This resonance ensures that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This seemingly simple relationship is the result of gravitational forces that prevent the 2 planets from ever being in the same place at the same time. This unique resonance has been studied for decades and is believed to play a crucial role in maintaining the long-term stability of Pluto's orbit. However, as Tyson and Kaku have suggested, while these forces are stable for now, Pluto's orbit could become more unpredictable in the future. The solar system is certainly not a static system. It's a place of constant movement and gravitational influences. Even small changes can have significant long-term effects. The three-body problem, which deals with predicting the movements of 3 celestial bodies under mutual gravitational attraction, is a crucial area of study when it comes to understanding Pluto's future. In the case of Pluto, Neptune, and the Sun, this problem suggests that while the planets' interactions currently prevent a crash, their gravitational pulls could shift in unpredictable ways over the millennia, potentially causing drastic changes to Pluto's orbit.